Welcome to the Explainer. Today we are cracking the code on Cambridge IGCSE Physics 0625. We're zeroing in on Momentum 1 exam mastery, and we're skipping the fluff. Let's just jump right in, shall we? Okay, let's dive into this. Instead of starting with some dry, boring textbook definition, I want to pose a real challenge. What physical effect, measurement, or prediction actually depends on you understanding momentum? Think about a massive dump truck trying to slam its brakes at a red light, or picture two ice skaters pushing off from each other on a rink. Fun fact, those ice skaters are literally demonstrating the exact same physical principle that keeps rockets flying through the absolute vacuum of space. Crazy, right? If we want to predict how far that truck is going to skid, or how fast those skaters will glide apart, we absolutely need momentum. By putting the physical effect first, momentum stops being just some random vocabulary word you have to memorize, and it transforms into a real, practical tool we can use to decode unfamiliar, complex scenarios. Now, to really lock this knowledge in, there's a brilliant little trick we can use. Start with everyday language before you even touch the precise physics vocabulary. It's a huge trap to just memorize P equals mv right out of the gate. Don't do it. Instead, start with a concrete everyday example, kind of like that heavy dump truck we just talked about. We need to understand that heavy, moving object in normal, everyday terms first. Once you've got a firm grasp of the real-world scenario, then, and only then, do we bring in the formal symbols and definitions. Bouncing back and forth like this ensures the vocabulary actually means something to you, rather than just being a random alphabet soup you might forget under exam pressure. So how does this micro-topic act as a gateway to the bigger picture? Well, mastering momentum is really about guiding your thinking through 4 linked steps. It's kind of like unlocking a giant puzzle. First, identify the quantity. Are we talking about mass, velocity? Second, state the relationship. How exactly do these quantities interact with each other? Third, explain the underlying physics. What's the actual fundamental mechanism at work here? And finally, step 4, connect it all back to a real-world observation or experiment. I can't stress this enough. This sequence is incredibly powerful for IGCSE-style physics. The absolute highest scoring exam answers are always the ones that tie deep theoretical understanding directly to a practical application. And that brings us to a golden rule straight from our source material. Insist on cause and effect rather than isolated facts. Whether we're dealing with fields, forces, particles, or momentum itself, examiners absolutely do not want a regurgitated list of memorized trivia. No way. They want to see the why and the how intimately connected. If the mass of an object increases while its velocity stays exactly the same, what is the exact effect on its momentum, and more importantly, why? Understanding this cause and effect chain is the ultimate secret to transforming a mediocre, middle-of-the-road answer into a top-tier response. We have to prove to the examiner that we know how a change in one physical property directly causes a change in another. And this brilliantly illustrates how the cause and effect mindset applies directly to reading and interpreting physics graphs, which, as we know, are a massive part of the 0625 syllabus. When a topic like momentum involves a graph, we can't just stare at the numbers. We have to stress the physical meaning behind the visual representation. Ask yourself, what does the slope mean physically? Is it acceleration? Is it a rate of change of momentum? What does the area under the curve represent? What does the direction of the line indicate about the vector quantities we're looking at? And what does the overall shape actually signify? Remember, every single line on a graph is telling you a visual story of cause and effect. You just have to translate it. Let's step outside the classroom for a second. It's genuinely fascinating how momentum applies in the real world. We see it in vehicle safety features like airbags and crumple zones, in transport logistics, energy systems, and even cutting-edge medical technology. Now, being able to simply name a real-world application is fine, but explaining why the physics helps us predict or improve outcomes, that's where the magic really happens. For example, how exactly does extending the time of a collision reduce the force on a passenger? That's not just an exam question, folks. That is literally momentum saving human lives in real time. All right, let's bring this all back to your exam papers. There's a massive difference between a weak approach to answering a question and what our source calls the safest method. The weak approach, that's heavily relying on rote memory, essentially just vomiting a formula onto the page and praying the examiner figures out what you mean. Please don't do that. The safest, most effective method follows 4 precise steps: definition, relationship, explanation, and application. First, define the concept. Second, state the mathematical or physical relationship. Third, explain how it works. And fourth, apply it to the scenario given in the prompt. This structure is basically a foolproof way to ensure you're hitting every single mark on the examiner's rubric. So, the crucial point here is avoiding the mistakes that trap so many of us. Honestly, it's incredibly easy to fall into these common exam pitfalls. First up, writing a perfectly correct formula, like P equals MV, but totally forgetting to explicitly explain what those variables stand for in the context of the question. That is literally throwing away easy marks. Second, quoting a process without linking it to a physical effect. We shouldn't just say the objects collide. We need to explain how the momentum transfers during that specific collision. And third, giving an example without showing why the physics applies. If you mention a seatbelt, you have to explicitly link its function to the change in momentum over time. We can counter all these errors simply by keeping our reasoning tightly connected to the physical reality of the situation. To make sure all of this actually sticks in your brain, try using these 4 core revision prompts whenever you're reviewing Momentum 1. 1. What is the core idea? 2. What changes physically in the system? 3. What quantity or graph shows this change? And 4. Where is it used in the real world? And here's a highly effective, albeit slightly weird trick for studying. Actually speak the answers to these prompts out loud. Seriously, it feels a little silly at first, for sure. But if you can clearly and confidently articulate the answers out loud to an empty room, your grasp of this micro-topic is definitely secure enough to handle any short answer or structured question Cambridge can throw your way. Let's wrap up with a final thought and see how this builds your overall exam readiness. Here's a question for you. Can you explain the physics behind momentum using a clear cause and effect chain in a real-life example? Don't just nod along right now. Really think about it. Can you trace the exact sequence of events from the mass and velocity of an object through an interaction, all the way to the final outcome? This is the ultimate test of our application-first mastery. So take this question, grab a piece of paper, and try writing out your answer using that definition, relationship, explanation, application method we discussed today. Thank you so much for joining me for this explainer. I'll see you next time as we continue to break down the fascinating rules of the universe.